So again, I'm Donna Crawford, Associate Director of Computation at Lawrence Livermore National Laboratory. I am here on this conference call with a number of our partners, and we will make introductions as each one speaks. Livermore is partnered with Lawrence Berkeley and Oak Ridge National Laboratories to support the HPC for Manufacturing program. The Department of Energy laboratories have 5 of the top 12 high-performance computing systems in the world and a host of other computers. These systems range from industry-standard capacity clusters to cutting-edge supercomputers. We also have state-of-the-art infrastructure comprised of computer centers and associated networking, visualization, file systems, performance tools, etc., and operations support to reduce the complexity of using these systems. More importantly, the labs have deep expertise in using high-performance computers to help solve complex problems from multiple domains. And our computer codes have been experimentally verified. The labs are providing access to their computing facilities and expertise in an effort to enhance economic security. And this program is an example of how the national labs effectively partner with one another and with industry. Now I would like to turn it over to David Danielson, Assistant Secretary for Energy and Efficiency and Renewable Energy within the Department of Energy. Dave?
Well, thanks, Donna, and thanks for your leadership and really working together as a team to launch this exciting new initiative for the country and for our manufacturing competitiveness. Good morning, everyone. I want to thank you all for joining today. I'm David Danielson. I'm the Assistant Secretary for Energy Efficiency and Renewable Energy at the Department of Energy. And my office is the largest single funder of clean energy innovation in the world, investing about $2 billion in American innovation this year alone. And one of our top key cross-cutting initiatives since I arrived about 4 years ago is the Clean Energy Manufacturing Initiative. And this is really an initiative that seeks to ensure that the United States leads the world in terms of inventing and manufacturing the clean energy manufacturing technologies of today and tomorrow, but also investing in innovation to help our existing energy-intensive industries become more energy efficient and more competitive so that they can lead globally as well. We're here today to really discuss one of the most exciting efforts we have focused on advanced manufacturing, on clean energy manufacturing, our new high-performance computing for manufacturing program, also known as HPC for MFG. This effort is led, as Donna said, by Lawrence Livermore National Lab, Oak Ridge National Lab in Tennessee, and Lawrence Berkeley National Lab in Bay Area, with Lawrence Livermore and Lawrence Berkeley both in the Bay Area. HPC for manufacturing, which was really created by our Advanced Manufacturing Office and my Office of Energy Efficiency and Renewable Energy, or EERE, really couples the entrepreneurial spirit of leading U.S. manufacturers and innovators with the world-class resources and the brilliant minds at our national laboratories to apply the amazing cutting-edge tool of high-performance computing to help them overcome and address some of their greatest manufacturing challenges and opportunities. And these innovations really hold the potential that we're talking about today to develop exciting, high-impact new manufacturing processes and new materials that can drive American competitiveness in the years and the decades ahead of us. And I wanted to put a little bit of context. Through our Clean Energy Manufacturing Initiative, we've been very active. ERE and DOE have been a big supporter of the President's National Network for Manufacturing Innovation, where across government we will have established by the end of this administration 15 major manufacturing innovation centers, major regional industry and research institute collaborations in a number of areas. Established not only the National Network for Manufacturing Innovation, or NNMI, but the other important model that we've established in our research infrastructure for manufacturing is what we call manufacturing demonstration facilities, or MDFs. The first one we established was at Oak Ridge National Lab, focused on 3D printing. It's been tremendously successful. And what we're talking about today, the HPC for manufacturing facility, is our second manufacturing demonstration facility. And these MDFs, or manufacturing demonstration facilities, are really facilities at our national laboratories that are really designed to foster an open exchange of best practices and know-how bringing together our high-performance computing capabilities and other amazing capabilities at our national labs with advanced equipment providers, manufacturing experts, and companies that want to use these technologies to make advanced new products. And I also wanted to point out that at the Department of Energy and through a Clean Energy Manufacturing Initiative, it's really been all about engaging with industry and really understanding the needs that they have as we build these programs. And this program idea, the high performance computing for manufacturing, really did grow out of a very comprehensive public-private partnership we've had with the U.S. Council on Competitiveness, the American Energy and Manufacturing Competitiveness Partnership. And it was about, in 2014 was really the nexus of this idea of this high performance computing for manufacturing demonstration facility. And so today is really the result of a lot of great work that's been done in engagement with industry and with the Department of Energy together. We have a list of these awardees that we're announcing today. We're going to be awarding $3 million in a first round of funding to 8 companies who are partnering with us on 10 HPC high-performance computing projects to address their key manufacturing challenges. These collaborations will apply advanced modeling, simulation, and data analysis to industrial processes and materials to lower production costs and shorten the time it takes to get new products to market. And not only does this program lower the cost of entry for U.S. manufacturers to use modeling and simulation technology for competitive advantage in the USA, but it also paves the way for further energy-efficient manufacturing practices and ongoing development of advanced clean energy technologies. And you can see the list. I'm not going to go through all these projects, but I think there's a wide diversity of exciting projects from global foundries in upstate New York, developing a next-generation microchip that will allow for dramatically lower energy usage. And the high-performance computing will be used to model the electron flow and the heat generation at an unprecedented scale to help them design that technology, all the way to a small business called Zoom Essence in Kentucky, who's going to use high-performance computing and advanced computational fluid dynamics to model a completely new way of drying food, which is a huge energy user in this country. And so that game-changing new technology can dramatically reduce the energy footprint of our food industry. And that's just a couple of those projects. You can see here that overview. But I did want to just hit on a couple of specific projects very briefly. The first is a project we have at GE Aviation. General Electric in this project is partnering with Oak Ridge National Lab and Livermore to improve the efficiency and component life of aircraft engines through design optimization and the application of high-performance computing and computational fluid dynamics to really understand how these gases and reactions flow and design a next-gen, much more efficient jet engine. More than 35 billion gallons of fuel are used each year to transport airline passengers all around the world. And this initiative really holds the potential of helping to reduce that fuel usage dramatically, reducing costs, and increasing engine lifetime and reducing emissions. The other project I wanted to mention is a project we have with Procter Gamble. Another example, so this is an example where Procter Gamble is going to be working with Lawrence Livermore National Lab on an area that maybe you don't always think of when you think of energy, but the pulp and paper industry is one of the biggest energy users in the country. And this project will use high-performance computing and modeling of paper and paper manufacturing processes to reduce the amount of high-energy pulp that actually goes into this paper by up to 20%, which can dramatically reduce the energy that's going into this industry and save companies like Procter & Gamble a whole bunch of money in the process and reduce costs to customers. These are just a couple of examples of the exciting work that we wanted to highlight to you that's happening through this initiative and this first major announcement related to this new HPC for manufacturing program. President Obama and other world leaders recently committed to doubling down our investments in clean energy R&D over the next 5 years through the Mission Innovation Initiative. It's clear that solving our climate and energy challenges will require technological innovation, including the development of some technologies that we haven't even come up with yet. Partnerships like HPC for MFG are what will allow us to develop the breakthrough technologies that we need to develop to stay globally competitive in the race for new and innovative sources of energy. And we're just getting started. Over the next few months, we will be announcing a second round of funding of $3 million available through the HPC manufacturing program to qualified industry partners to participate and compete for. I really want to emphasize that high-performance computing is truly a competitive advantage for the United States, and it's not just what our national lab partners call the big iron, the big computers, but it's these big brains and these amazing and talented people we have in our labs who can actually help advanced companies use these facilities in a way that can really drive their competitiveness and drive their ability to develop new products in the clean energy sector. So with that, I'm going to turn over the call to my friend and colleague, Dr. Mark Johnson, the director of our Advanced Manufacturing Office, which is the sponsoring office for this exciting new program. And Mark's going to discuss his team's work on this initiative and some success stories that we've already had from our first crop of program participants, where we made some seedling investments even in advance of this exciting first major call for funding and the $3 million and 10 projects we're announcing today. With that, let me pass it over to you, Mark.
Thank you very much, Dave, and thank you for everyone joining us here today. I'm going to give you a little bit of background on how we wound up standing up the HPC for MSG program in partnership with the National Lab. Some of the work we did to really try to ensure that in unleashing the incredible world-class capability in HPC that we have within our National Lab system, that was really targeted to work most effectively with manufacturers in solving these manufacturing problems. So as you pointed out, over the past year, what we first did, in order to ensure that this research work we were doing would really have the highest impact, we worked together with a number of manufacturers in the manufacturing sector to really craft up what would a public-private partnership look like, and really in identifying what the category of problems are and technical challenges that manufacturers are really working on and trying to use, and how we can wind up applying the expertise and research capabilities of our national labs to solve these problems most effectively. So Lawrence Livermore National Lab, Lawrence Berkeley National Lab, and Oak Ridge National Lab all have world-class technical capabilities and expertise to solve these complex problems that the industry is facing, and linking that up together with the high-performance computing was the effort we went through over the past year. Just to give you a little bit of background on the piloting of this, we had 4 seedling projects that we went through over this past year just to be able to demonstrate the range of capabilities that are possible in this area. The 4 projects are listed here. Just to give you an example of a few of them, if you look in the steel industry, for instance, we still wind up, in making a lot of our steel, we use steel-making processes like blast furnaces, and how you use energy in those processes really affects the outcome in how you wind up making that steel. So at Purdue at Calumet, they lead a consortium of steel manufacturers, and we worked with them to receive funding during the seedling round to use high-performance computing to optimize the blast furnace processes. A high-quality blast furnace computational model really has the potential to save both money in how they operate the blast furnace and also improve the productivity of that blast furnace operation, getting greater technical understanding of the operation. There's still 20 blast furnaces in the United States, and these new techniques may help steelmakers more rapidly adjust production to fluctuating market conditions, and can potentially allow for the factories to run more efficiently at a wider range of operating conditions. That both improves the energy efficiency and, as importantly, winds up helping protect and save American jobs. So, for instance, at U.S. Steel number 14, which is one of those blast furnaces, for every percentage point we shave off the coke rate in a blast furnace, we reduce the total coke consumption and the carbon footprint by 8.5 million kilograms per year. This is based on Steel Association's rounding of the numbers on this, estimates on these numbers. But that's a huge potential impact on both improving the energy efficiency, reducing the carbon consumption, and also wind up really driving economic efficiency of these processes. On the other end, we're looking at, as Dave said, the paper manufacturing area is still a large energy consumer in the United States. There's a group called Agenda 2020 that winds up running a paper manufacturing consortium. They're using HPC to model how water flows through the pores of paper during the pulp and paper process and during the pressing process. This is a very energy-intensive part of that process. And there's a specific area of that called the re-wetting process of pulp and paper during the pressing that's the most energy-intensive part of the paper-making industry. And developing a really high-resolution computational model of this allows optimization of that process and could potentially save the paper industry up to about $240 to $400 million annually. So this really can wind up having impact in a lot of these energy-intensive industries. Now going to some of the more emerging technologies that are out there, we work with a company called Sora. It's a startup company that's is one of our first seedlings, and they work with Lawrence Livermore National Lab. And Sora develops high-fidelity models for the manufacturing of the materials that are used for the very high-efficiency LED lighting that's coming out right now, and really trying to get around the elimination of the trial and error approaches in the experimentation of the manufacturing that they wind up doing, and having really strong predictive models for how they can scale to even larger sizes, driving down the cost in those areas. With that in point, I'd like to transition over to Mark Devlin from Sora, who's joined us today to go into some of the impact of this project on his company. Mark?
Thanks, Mark. Sora is a solid-state lighting company manufacturing a range of LED-based products such as MR16 lamps, which are shown on the next slide. Like LEDs manufactured by our competitors, Sora's LEDs are based on a semiconductor material called gallium nitride, or GaN for short. Unlike our competitors, however, our LEDs are fabricated on native gallium nitride substrates rather than foreign substrates such as sapphire. Our founders, led by Nobel Prize-winning professor Suji Nakamura, became convinced some years ago that the use of native GaN substrates would be the key to unlocking greater performance from GaN-based LEDs. Today, Sora's GaN-on-GaN LEDs emit 5 times the light per unit area as other LEDs, with unique full-spectrum color, enabling excellent rendition of all colors from whites and violets to deep reds. However, the GaN substrates we purchase overseas today, developed originally for Blu-ray laser diodes, are rather expensive, and their crystal quality is not yet as high as better developed materials such as silicon. With generous assistance from ARPA-E, an agency within the Department of Energy, we've been able to develop a novel crystal growth process where GaN feedstock dissolves in superheated ammonia, is transported by free convection, and precipitates on seed crystals. Today, we're able to fabricate prototype 2-inch single crystals and wafers with state-of-the-art quality, as shown at the lower right. This process can be scaled up to larger diameters and to high-volume, cost-effective manufacturing. It can be transformational for new generations of GaN-based power electronic devices, as well as for LEDs. In order for this to happen, however, we need to better understand and control the fluid dynamics within the crystal growth environment. This process operates at high pressures and temperatures, and so it's not practical to observe the crystal growth process directly. Therefore, we're delighted that the DOE has funded Lawrence Livermore to develop an advanced model for the fluid dynamics and chemistry to take place in this process. If they're successful, this will greatly accelerate optimization and scale-up, and we hope enable large-scale US-based manufacturing of GaN substrates, as well as of advanced LEDs, lasers, and next-generation GaN-based power electronics. Thank you.